Okay, so I'm going to get started. This is the fourth and last talk of this series of talks on distinguished representations, and it will be dedicated to the relative trace formula, which is a distribution on the group G, which is developed by Jacquet and people he worked with at the time, and designed to study period integrals on automorphic forms. Okay, so it's another global talk. G is a reductive group defined over a number field. And for the sake of this talk, it will be convenient to just adopt a notation that's becoming more and more standard. G in brackets, in square brackets, is the automorphic quotient of G of the Adele's mod rational points. Okay. So what is the data that's coming into the relative trace formula? So the data is a 5-tuple. The group G and two subgroups, each of them coming with a character on them. So Hi is a subgroup. It's a closed subgroup. And Chi is a character of the automorphic quotient of Hi. So if we start with any test function, right, so this I'm using Johann's notation. This is really the smooth functions of compact support on the Adeles of G. Then the relative trace formula associated to the data D at F, well, it's an integral, double integral, and the sum of F of, we write it this way, H1 inverse gamma H2, Chi1 H1, Chi2 H2, dH1 H2. Okay, so we are summing over all rational points, and we're integrating over the automorphic quotient of H1 cross H2. Okay, in other words, the function we're integrating is the standard kernel function that you have seen in Johann's talks when he spoke about the standard trace formula. And in the trace formula, you integrate it over G embedded diagonally in G cross G in order to compute the trace. Here instead, you integrate it over H1 cross H2. Okay. So I should say that unlike Arthur's relative trace formula, the relative trace formula was not developed in this full generality. So even convergence issues here occur. So just for today, to make things well defined, let me assume that at least one of the automorphic quotients is compact, okay, to make everything more explicit. Okay, so we have seen in the talk about the trace formula that this distribution can be expanded geometrically and spectrally. And in this case, the geometric expansion well, it's no longer over conjugacy classes, but rather over double cosets. Okay? So just formally, if I look at the kernel function, right, remember, Johan wrote it as a sum over conjugacy classes. It's a sum over G, then you can divide this sum into any disjoint union of sets that give you all the rational points. So we instead expand it along double cosets. So we can write it as a sum of over eta of, and let's say a sum over alpha 1 and alpha 2 of f of x inverse alpha 1 inverse eta alpha 2 y, right, where eta is summed over double cosets. And alpha 1 and alpha 2 are taken in H1 cross H2 mod stabilizer. In other words, over the double coset. Right? So accordingly, you can write down the contribution of each one of these pieces. So just formally, one can write down the relative trace formula, where I can take out the sum over double coset, right? And then we have to integrate over the automorphic quotient of H1 cross H2, and then sum up over H1 cross H2 mod the stabilizer. So I can do the integration, join the integration and the sum, and we obtain an integral over H1 cross H2 of the agels mod the rational points of the stabilizer of f of H1 inverse eta H2, chi1 of H1, chi2 of H2, dH1 H2. Okay, so this is all a formal computation, and we can go further and first start with an adelic integration. So this is fairly similar to what Johan did in his lecture, except there is an extra phenomena happening here coming from the characters. So I can integrate over H1 cross H2 adelic mod the adelic group of the stabilizers and then integrate over the automorphic quotient of the stabilizer. But remember that clearly this part of the expression of the integrand is not going to depend on anything in the stabilizer of eta, right? So this integral really becomes an integral over the characters, chi1 t1, chi2 of t2, dt1 t2, and then we have an outside integral f of h1 inverse eta h2, chi1 of h1, chi2 of h2, dh1 h2. This is not me, right? Okay, so if we just look at the inner integral, this is an integration of some character over a group. Under our assumption, it's a compact group, so it's at least well defined, but the only way that it's going to contribute is if the character is trivial, right? So this leads us to the notion of relevant orbits. So eta, or its double coset, is D relevant if chi1 cross chi2, when restricted to the stabilizer, is the trivial character. Okay. Okay, so the geometric expansion is really a sum over all the D-relevant orbits of, well, now the integration over the stabilizer is just of the identity. So it's, let me denote this by V eta, and there is an orbital integral, which is really an adelic integration. And remember, the measure on an adelic set is a product of local measures. So these are really products at all places of orbital integrals on the local spaces. Okay, so here, V of eta is the volume of the automorphic quotient of the stabilizer. While the orbital integral is the integral over h1 cross h2. Right, it's the integral over the double coset mod h1 cross h2 stabilizer of f h1 inverse eta h2 against the characters. Okay, so this can be written as a product over all places of local orbital integrals. Okay.
When you write the times, you mean temporal. I want that, right?
Yes. Okay. Thanks. Yeah, I definitely don't mean parabolic induction. Okay, so I'm not going to be too explicit about the spectral expansion, but let me just say some generalities and at least relate to the relative trace formula with this property of distinguished representations. So the standard kernel function also has an expansion which is based on Langlands spectral expansion. So Arthur wrote down this as a sum over cuspidal data of components coming from this cuspidal data, okay, which I'm not going to explicate in general, but I'll just let you know what they are when the cuspidal data is actually a cuspidal representation of G. Okay, so formally, we just have that the relative trace formula at F can be expanded along cuspidal data by some distributions where of course this distribution is just the integral of the chi component in H1 and H2 against the character. Okay, so if pi is an irreducible cuspidal automorphic representation, then kf pi can be expanded as follows. So it's a sum over the set, I'll denote by OB of pi. So f acting on the automorphic form phi and evaluated at x, and phi evaluated at y, where we actually sum over. So if I want to be precise, this is an orthonormal basis well, not quite for pi, but rather for the pi isotypic part in the cuspidal spectrum of G. Okay, so, so if pi has multiplicity 1 in the cuspidal spectrum, this is just an orthonormal basis over pi. But in general, pi may have more cuspidal realizations in the spectrum. Okay. So if we integrate over H1 cross H2, well, what we get is a sum over the orthonormal basis of a product of period integrals. Sorry, get back to the notation from yesterday. With a complex conjugation. Actually, so this distribution, the contribution of pi to the relative trace formula, okay, this is really the global analog of the spherical distributions that showed up in the last 10 minutes of Fiona's talk this morning. Okay, so remember these were distributions that were defined by two invariant linear forms on a representation, and in the automorphic case, the two linear forms are the period integrals. So the only way this distribution is not going to be vanishing, it's going to contribute to the relative trace formula, is if these period integrals don't identically vanish. Right, so b pi is not identically 0 if and only if, well, not quite pi, but the isotypic part of pi is both hi chi I distinguished. In other words, there is a realization of pi which is distinguished by both subgroups. Okay? So this should give you at least the intuition that this distribution, the relative trace formula, it picks up those automorphic representations that we are interested in when we study period integrals, the ones that are distinguished. Okay, so maybe the strongest applications of trace formulas in general, as we have seen in the Jacquet-Langlands correspondence, is when you compare between two trace formulas. And the relative trace formula has been designed in order to be able to compare between trace formulas and study periods on one group by information on another group. So what I'm going to do for the rest of the talk is show you one of the first comparisons that has been worked out in general rank. So this is a comparison by Jacquet-Rallis. Okay, so the comparison I'm going to talk about, maybe it's not the one that is the most famous Jacquet-Rallis relative trace formula comparison. There is one in the context of Gann-Gross-Prasad for unitary groups that is now very popular. This is a much older work. So what I'm going to take is two different data. One of them is the group will be GL2N. And the subgroups are the symplectic group with the trivial character and the maximal unipotent with some character. And the other data, we call it data prime, it will be GLN with, okay, so for some technical reasons, I'm going to take the maximal unipotent, but once transposed, and with the transposed, so the transposed now a non-degenerate character, and the standard unipotent with a non-degenerate, with the same non-degenerate character, but transposed. Okay, so I'm going to write down the expansions in each of these cases first, and then explain how what is a comparison between these two relative trace formulas based on. So this example is designed in order to study SP distinction in GL2N, where in the GLN case, the relevant distinction is really being generic or having a Whittaker functional, which is for GLN better understood. Yes?
This sum of the two periods is not very known.
So as Fiona explained, these spherical distributions, they're really generalizations of matrix coefficients. Okay? So these are matrix coefficients with respect to these two linear forms. Okay? So to say, so this is really linear independence of matrix coefficients. To say that a matrix coefficient is not zero is to say that the vectors that define it is not zero. Yes. So I meant as a distribution, or oh, thank you, yes. Thank you. Okay, so I'm going to start with the easier side, which is D prime. Okay? And the trace formula, the relative trace formula in this case is often referred to as the Kuznetsov trace formula. Okay, so I'm going to keep the primes everywhere for the D prime data. So G prime is GLN. N prime is a group of upper unipotent matrices inside G prime. And psi prime, the generic character of an element U, is, say, psi node of U1, so a sum over the simple root elements, where psi node is a non-trivial additive characters. Okay, so it's in characters of the Adels mod F. So the data D prime we're using, as I have written, is G prime N prime transpose with the character psi prime transpose, N prime, and psi prime. Okay. So you can see that geometric expansion is related with double cosets. In this case, this is related with the Brouhat decomposition, right? Yes.
Certain points you needed that the volume of this H1 times H2 adelic subeta to be finite.
Yes.
So it's that. So I cannot use too many pairs of H1 and H2, right? I have to have this condition.
So, okay, I made this assumption in order to avoid these issues.
In the example, I see it works.
Yeah. So otherwise, just like in the trace formula, one needs some kind of regularization in order to define the distribution. Yes. So all of this should be definable, but one has to find the right setting. And in general, the right setting is not yet available. Okay, so for the geometric expansion, let me denote by A prime the split torus of diagonal matrices. So the normalizer of this torus is just scaled permutation matrices. Right, this can be written as W times A, where A is in the torus, and okay, W is a permutation matrix, essentially a permutation on N. Okay. So the Brouhat decomposition identifies the double coset space with the normalizer of the torus. And the question is, what are the relevant orbits? So just, again, to have a baby warm-up exercise, let's do some GL2 computation. Okay, so the normalizer of the torus, so we look at n equal 2, and now the normalizer of the torus is really the torus itself union with A prime W. Put the W where W is the long while element. So just because I chose double cosets with respect to n prime and n prime transpose, the diagonal matrices lie in the open Brouhat cell, right? This is the big cell. So if I choose A in A prime, then the normalizer of A is trivial, right, in the open broad cell. So all of these are relevant. Okay. But if I take, say, A to be A1, A2, so I can make a computation, just multiply the matrices 1x1, A1, A2, 1y1. So we get whatever we get. So it's xa1 plus ya2. And we see that the stabilizer of WA is all matrices of the form, so 1x1, 1y1, where, well, A1 x plus A2y has to be equal to 0, right? In other words, y must be minus A1 over A2 times x. Okay, so if we compute our character on the stabilizer, so if I plug in psi prime transpose cross psi prime at a point in the stabilizer, what we get is the additive character evaluated at, well, 1 minus A1 over A2 times x. Right. So for this to be trivial for all x, we must have whatever here in the parentheses has to be 0, right? So WA is D-relevant if and only if A1 is A2. So this gives an idea of how relevant orbits are actually described in general, and let me give the general picture. D-prime relevant orbits okay, so I'll denote by Wn the long vowel element in GLN. And if we have any standard Levy, GLN1 up to GLNK, then let me denote by Wm the longest vowel element of the Levy. Okay. And by Zm the center of the Levy. A1. So scalar matrices in block diagonals. So you can see that a generalization of what we just described is that the double cosets that are D' relevant are in bijection. This is a complete set of representatives with WMA, where M is any standard parabolic, standard levy of G prime, and A is any element of its center. So this is if you want to work this out yourselves, this is an exercise in matrix multiplication, but maybe a fairly complicated one. Okay, so one can also actually write down explicitly or more explicitly the orbital integrals. So we have a decomposition of the unipotent radical of n prime as the portion that lies inside M times the unipotent radical of the parabolic with levy M, right? So UM is this unipotent radical. And what I'm going to call the Kuznetsov trace formula, right, which is the relative trace formula for the data d prime, well, this is the sum over all M and the sum over all A in the center of M of the orbital integral of F at the orbit representative for the relevant orbits. Okay, and let me write down the orbital integral. Okay, so it's a simple computation to compute that the stabilizer of WMA is essentially n prime intersect M, and then the orbital integral just explicitly looks like this. So in one variable, we integrate over n prime, and in the other variable, we integrate over the quotient of n prime by the stabilizer, which is n prime intersect M. That's the unipotent radical of the parabolic with levy M of F of H1 inverse WMA H2 psi naught. So I guess I should put a transpose here because I'm integrating over n prime transpose, and psi naught of, okay, let me put U's just for the unipotent elements. Psi of U1, U2, du1, U2. Okay, so you may wonder where the volume element disappeared. Well, all of these are integrals over unipotent subgroups, and one can normalize, these are all root subgroups, and one can normalize the measures so that all these measures are going to be 1 in this case. Okay, this is compact quotient.
You are not in the situation where the stabilizers are compact?
Yes, I am.
Do something else.
This is a situation where stabilizers are compact. This is the automorphic quotients. We're not in the local world now. Okay. So Adele's mod F is compact. Okay, so in this case, one can actually write down what the, at least morally, what the spectral expansion looks like. So the form of the spectral expansion of the Kuznetsov trace formula should be of the following form. So one sums up again over all Levy subgroups and over all cuspidal representations. And there is one has to take into consideration the continuous spectrum. So if you're Levy, so there will be some integration over the unitary axis of the spherical distributions associated with the induced representations. So what comes up into the picture here is Whittaker coefficients of Eisenstein series. Okay, the induced representations entail Eisenstein series, and the period integrals are the Whittaker coefficients. Okay, so let me get to the other side. I'm going to rewrite what I just erased, a relative Kuznetsov trace formula. So now G is GL2N, right? H1 is SP2N, and I'm going to write N for the unipotent radical inside G. And the character I'm defining, so psi of U1 and U2, and whatever is here, is the generic character applied to U1 times U2. Okay, where U1 and U2 are GLN unipotent elements. Okay. So as I wrote down earlier, this is a degenerate character. There is constant integration on the unipotent radical of the NN parabolic. Why do I take a degenerate character? Well, we know that a relative trace formula is only going to detect distinguished representations. So we want them to be both SP distinguished and distinguished with respect to N and this character. And we already know from the previous lectures that generic representations, the ones with are N distinguished with respect to a non-degenerate character, cannot be SP distinguished. So if I chose a generic character, the relative trace formula in this case would be 0. Okay? So in order to have non-empty information, we're taking the degenerate character. And again, one has to analyze double cosets. Okay, so again, the data D is now G. So H, let me call SP2N H, the trivial character, N, and the degenerate character. Yes?
Sorry, I didn't hear. So you cannot take the generic character. So what is the character you take?
I could take the generic character, but I would get 0. So what I'm taking is this character, which is constant on the unipotent radical of the NN parabolic. Okay? So if you think about it spectrally, the representations that will appear there will have to have a constant term with respect to this parabolic. Okay. So as we have seen in the local analysis, when we have the symmetric space G mod H, it is sometimes easier to think of its embedding into G, the embedding into G. So this is the symmetric space X that I was talking about in the local case. Okay, so we have seen that already. Let me just write it down briefly. We can identify G mod H with the space of skew symmetric matrices in G. Right? So we just take a right coset and send it to G transpose JG, where J defines as the symplectic group. And then we get an identification of orbits. Also, we get a map from the space of functions on G. Well, if we just integrate over H, get a map to a space of functions on X. And this is a surjective map, right? If we take F here, I can send F to phi, where phi of G transpose JG is the integral of f of GH dH. So we can expand the relative trace formula now in terms of a distribution on functions on X. Right, so really, the relative trace formula on F, once you expand things, you see that it equals the integral over the automorphic quotient of n of phi of n acting on X, so summing up over all rational points in X, phi of n acting on X. And so this is sort of a relative analog of a kernel function, and this is integrated against our character. Okay, so if you want to do a geometric expansion, well, we identified G mod H with X. So we can identify the double coset space with n orbits on X. And the lemma on good orbits that I discussed in the local case showed us, or essentially tells us in this case, that the good orbits here, so this actually follows from work of Springer on involutions, that this is the intersection of X with the normalizer of the torus, with the sign permutation matrices. So this is a very explicit set. One can write down exactly which scaled permutations appear there. This is WA, where W is an involution that conjugates A to minus A. Okay. So here's an exercise that will relate the geometry of this double coset with the geometry of the space for the Kuznetsov trace formula. Maybe before that, let me just remark that, well, we are only interested really in relevant orbits, so we shift the property of relevant orbits to X, right? What this means really if we look at the trace formula, so x is relevant means that the character psi is trivial on the stabilizer of x. Okay. So we want to study relevant orbits.
Excuse me, which one did you say follows from Springer?
This. Okay. Yes. Mm-hmm. Okay, so if we take a skew symmetric matrix, which is of the following form. Okay, so this is in X. So it is relevant with respect to D, meaning it satisfies this property, if and only if the matrix G, remember this is a GLN matrix, is relevant for the D prime data. Okay. So there is a relation between relevant orbits in the two settings. And in fact, using this exercise, this is one step, and one can get a consequence is that there is a bijection between relevant orbits. Okay, so if we look at G mod H mod N, right, D relevant, we know this is bijective with X mod N, D relevant. These are all matrices of the form WMA minus WMA, where M is a standard levy of G prime of GLN, right? And A is in the center of M. And this is bijective with the relevant orbits in the prime setting. Okay. So we have a basis to compare between orbital integrals. Okay. Okay, so now the relative trace formula looks like this. It's a sum over M and a sum over the center of M, where of some relative trace formula, let's say at F, is of the orbital integral of F at this element, while the Kuznetsov trace formula at, say, a function f prime on G prime is a sum over the same index set of orbital integrals of f prime on WMA. Okay. So if we could find enough functions for which we have matching of orbital integrals, then we can compare between the two relative trace formulas. Okay, so I will not have too much time to tell you precise results. What Jacquet-Rallis actually showed, let's say essentially, is that for every f, a function on GL2n, there exists f prime, a function on GLN, such that the orbital integral of f at g negative g transpose equals the orbital integrals of f prime at g. Okay, so the result is really a local result, so there is a smooth transfer almost everywhere, and the fundamental lemma in order to have identity of the local integrals almost everywhere at the unit Hecke element, and in fact for all Hecke elements. So this transfer is really a map in this case. So usually when we say transfer of orbital integrals, it's just an existence statement. For every f, there exists an f prime, and f goes to f prime is not a map. In this particular case, one could actually, for every f, construct f prime by some integration over f. So this is really the transfer of orbital integrals is actually a map. But the comparison has only been carried out in one direction. In order to obtain results from this relative trace formula, let me write in the other board, one actually needs the other comparison. So this has been done a while ago, and the reason why it was never worked out in full generality to extract the information of the relative trace formula is because one could use, as we have seen in the third lecture, one could use other methods in order to evaluate SP periods of automorphic forms. So one did not need, in this particular case, the relative trace formula. But let me just say what are the possible applications of actually working out the details of this relative trace formula for this case. So what will be the discrete contribution to this relative trace formula? Well, obviously we're not going to get any Cus forms, right? For two reasons. One is because no Cus forms are SP distinguished, and the other reason is that no Cus forms have constant terms that are not vanishing. So in fact, the only contribution is from representations of the form U rho 2. Okay. So at the end of the day, the type of information that can be extracted from the relative trace formula is that if f and f prime have matching orbital integrals, then the spherical distribution associated with this generalized Speer representation, the residue of Eisenstein series that we spoke about last lecture, equals the distribution of rho on f prime. Okay, so this is passable application if you want. Now this distribution, okay, it's a distribution of a Caspar representation of GLN with respect to two Whittaker functionals. So Caspar representations are generic, therefore it's not the zero distribution. It is distinguished by the Whittaker functional. So this is not a zero distribution. So we can take a function, a test function f prime, for which this is not zero. If we had the matching in the other direction, we can take f that matches and deduce that this distribution is not zero. But this means that U rho 2 is distinguished by the symplectic group. So we basically use the relative trace formula to recover the result of Jacquet-Rallis that we have seen in the previous lecture. Okay, so there are other methods to do this, but if anyone wants to get into this subject, this is a simple enough example that one can use it as an exercise to get introduced into all the techniques and methods necessary and maybe work out the details that have never been worked out in this example. Okay, so I think that's a good place to finish.